Good afternoon. I'm Tim Sever. Today we're going to be looking at an example of the definition of derivative through the limit process. So for this problem, for f of x equal sine x, what we want to do is show that the derivative at x would be cosine x. And we do this by using the definition of the derivative, which is what we're going to do today. So we know by definition the derivative of f at x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. So this is what we call the difference quotient, which is the slope of the secant line of f. The limit, of course, as we know, is the instantaneous rate of change, or it's the slope of the tangent line to f at x. So let's carry on and see what we get. All right, so f of x plus h is just sine of x plus h because f of x is equal to sine x, and we subtract f, which again is sine x. We get this limit. Now, of course, you can't evaluate by simply plugging in, because of course you'd have 0 on the bottom. And if f is continuous at x, and if it's not, it wouldn't be differentiable. But if f were to be continuous, then of course the limit as h goes to 0 of f of x plus h would go to f of x. So then you would have f of x minus f of x on top as well, which would be 0 over 0 in indeterminate form, which means in every one of these settings you would have more work to do. Okay, so to complete this problem, we use the well-known sign expansion for sine of x plus h. Which I've just done. Okay, so what we've done, let's go to the side. We know from pre-calculus or trigonometry that the sine of x plus h is equal to the sine of x cosine of h plus the sine of h cosine x. And that's what I used right here. Now we want to group, separate. The limit of the difference is the difference of the limits, again, provided both pieces exist. So we're going to separate this limit out, and we see there's a sine x in both of these pieces, so I'm going to not only separate it out, but I'll factor at the same time. Minus, and then you just have this plus, rather, this piece, the limit as h goes to 0 of this term Now let's recall h is going to 0, so in this setting the x's are constant. Constants can be removed outside of the limit, so the sine x will come out and the cosine x will come out separately, as these are two separate limit problems. And again, this sum is valid only in the case that these two limits exist, and that's what we're trying to determine. And we'll see shortly they are. All right, so we have the sine of x coming out because it's constant. Over here, the cosine of x will come out of the limit. Let's see what we have remaining. And we should see our favored two trigonometric limits appearing here in green. Okay, so this limit is well known to us. This limit goes to 1, so that limit exists. Partial justification for this separation. And of course, this limit is 0. Now technically, the way we wrote it, the limit is 1 minus cosine of h over h would be 0, but negative times 0 is 0, so this limit is 0. Since both of these limits exist, certainly the separation was justified as we've done it, so let's continue. Finally, we achieve sine x times 0 is 0. 1 times cosine x is cosine x. And we're finished with the limit process. So let's summarize and see what we've done. So, in summary, we've shown for f of x equals sine x, we've shown f prime of x is cosine x. So we've established basically, in essence, a derivative rule using what we would call the Leibniz or Leibniz notation, writing it a different way in terms of establishing a formula that we will commit to memory eventually. The derivative of sine is cosine. And we've done that via the limiting process. This was proof of this, which we could write as a theorem, but proof by using the definition of the limit, or what we call the limiting process, namely using this part right here. Well, actually, using this part right here, which is the definition, as indicated here, definition of the derivative. Once again, when doing a limit, in terms of good form, correct form, we write the limit at each stage. We don't leave it off. We write the limit at each stage until we evaluate. And again, I like to do the evaluation all at once, and this is the step at which we evaluated the limit. This limit was known to be 0, or technically minus 0, which is here. This limit is known to be 1, and here I didn't write it, but for effect this would be 1 times cosine x, which is just cosine x. All right, very good. Thank you.